Okay, so now I'm going to introduce the next set of definitions, and this is going to culminate in the real, true, honest-to-goodness definition of a Galois group, polynomial. It's amazingly difficult to find a simple explanation of the definition of a Galois group in the mathematical literature. Typically you'll see something like, well, it's the group of automorphisms of a field extension, of a splitting field, of a polynomial over a base field, which assumes that you know a lot of abstract algebra, and typically that's going to be difficult for a general audience to relate to, and I think that's a shame because this subject really could be a lot more accessible. So I'm going to introduce another set of definitions, and at the end I'm going to give the real, true, honest-to-goodness, serious definition of a Galois group, and then I'm going to give some examples in degrees 3 and 4 so you can see how it works in practice. Okay, so I'm going to be a little bit more formal here with my definitions now. So f of x is an integer polynomial. We're going to assume that it's monic. That means the coefficient of the highest degree of x is 1. We're going to assume that it has degree n, and that it's irreducible over the integers. That means it doesn't factorize into lower degree polynomials that are also integer polynomials. Similar to a prime number in number theory. The number 37 has only itself and 1 as factors. So this is going to be, we're going to be assuming that this polynomial is irreducible, does not split into smaller factors over the integers. Now I'm going to just I'm just going to go off on a tangent here about these coefficients, because in most, but if not all, websites and books on Galois theory, they will say that these coefficients can come from an arbitrary base field. And if you don't know what a field is in mathematics, just think of fractions. 4/7, 3/5, minus 2/9, or whatever like that. That's the set of fractions is basically the most obvious example of what's called a field in abstract algebra. You can basically you can add, subtract, multiply, and divide numbers, with the exception that you can't divide by 0. That's what a field is. And that's fine, except that the definition of a field in abstract algebra includes other structures as well, where there's a cyclic feature in the addition. So you can actually add the number 1 to itself a finite number of times and get 0. And that obviously does not happen in the integers of the rational numbers, or any extension of the rational numbers. That's a type of field known as characteristic P. And this is all very nice and it's very mathematically correct. However, I feel that it really adds, for someone who's first starting out on this subject and trying to grasp the essentials of Galois theory, it adds a layer of subtleties and complications and caveats that you really should not have to worry about when you're first learning. And so what I'd like to say to teachers of this subject is you don't have to do everything in full generality right off the bat. You can just start with integer polynomials. There's plenty, and I mean plenty, to talk about just within the realm of integer polynomials. You can get across all the main ideas of Galois theory. You can get into research level questions. You can just do an awful lot. And then if you want to talk about characteristic P at some point, that's fine. But I don't think it needs to be part of an introductory presentation. So that's my rant about that. So in this talk, all polynomials have integer coefficients. And then we're gonna define R1, R2 through Rn to be, again, this is a notation from abstract algebra, which essentially means any number that can be a root of a polynomial over the rationals. So, but basically what I'm saying here is we need to start with a given ordering of the set of roots of this polynomial, because we're going to be permuting them, so we have to know what order we're starting with. That's very important. Okay, so we have a polynomial, we have our set of roots in order, and now we're going to define a few more concepts here. An algebraic relation for f of x and the ordering R1 through Rn is a polynomial in n variables, again with integer coefficients, such that the value of that polynomial evaluated at this set of roots in this order equals 0. Okay, so we have a set of we have algebraic relations. They're multivariate polynomials, integer polynomials, and they have the property that when you plug in these roots in this order, you get 0. So, and I've made a few notations here. You don't have to worry too much. They form what's called an ideal in abstract algebra, which is a bit of an odd bit of terminology, but if you don't know what that means, you don't have to worry too much. I'm just noting this for future reference. And in the paper by Annick Valibouze, she calls this the ideal of algebraic relations. Okay. The symmetric or Vieta relations for f of x are, as we've seen the examples of in the previous slide, the elementary symmetric polynomials in n variables minus 1 to the k times the respective coefficients of f of x. So what we have here are generic, they are algebraic relations. They are generic for any polynomial. They generate an ideal. They are not an ideal by themselves in this polynomial ring. But they are generic for any polynomial. So the only way you would, literally any polynomial of a given degree is going to have these exact same set of algebraic relations. The only difference being, of course, the coefficients, which is the only way you tell any two polynomials apart anyway, is by looking at the coefficients. Okay, so this is as far as most polynomials go, and this is the interesting thing here. For this is not a mathematically rigorous statement, but it can be made rigorous, and it is true to say that for most polynomials, this is the end of the line. This is the entire set of algebraic relations, and of course, others generated by them in the algebra. But this is just simply generic, and for most polynomials, this is it. Where we get to the interesting part of Galois theory is that we find that for some polynomials, there are additional algebraic relations. I'm calling the Galois relations. Again, this is my terminology. I haven't actually seen this in the literature. But we have an additional set of algebraic relations, I'm calling the Galois relations, for f of x and the ordering of roots. These are the non-symmetric algebraic relations for that polynomial, if any. And that would be the ideal of algebraic relations, excluding any that are generated by the symmetric Vieta relations. Okay, hopefully you're still with me, because I'm coming to the final definition. The Galois group of f of x and the ordering R1, R2 through Rn is the set of permutations of R1 through Rn which preserve the Galois relations for f of x and R1 through Rn. So, in the general case, we can permute these roots any way we please without affecting, because for a symmetric polynomial, again, permutations don't affect the polynomial. You can permute the variables any which way you please. It does not affect the polynomial. Okay. However, if we have non-symmetric relations, we are no longer allowed to permute the variables any way we please. We have to respect the structure of these non-symmetric relations. So the Galois group of f is the set of permutations of the roots which preserve the Galois relations for f and the given ordering of the roots. Okay, so I guess that's a lot to take in. It's a bit abstract, and that's why I'm going to show you some examples next. So I'm going to show you an example in degree 3. And I got this example from this book by Henry Cohen, a course in algebraic number theory. And I will find the exact page number in a moment here. Okay. But I'll write out the example. F of x equals x cubed plus x squared minus 2x minus 1. Okay. The roots of this polynomial, approximately, are as follows. R1 minus 1.802. R2 minus 0.445. R3 1.247. Okay, now I said that in Galois theory we don't care about the exact numerical values of the roots. But we just need to know, we need to specify them in enough precision to be able to tell them apart. Obviously in this case 3 decimal places is plenty to be able to distinguish the roots. Okay, now we have of course the Vieta relations, which we do for any polynomial, so I'm not going to write those out again. But we do also, for this particular polynomial, have the following non-symmetric, that is Galois, algebraic relation between these roots. And it goes like this. R1 minus R2, R2 minus R3,